Okay, good day everyone. I am here to discuss with you another topic in our inorganic chemistry, and that is the acid-base equilibria. So it means also, or implies also, that we have discussed already different cations and anions. So we'll start from the illustration or from the picture at this portion. You could see here some dirty pennies or dirty coins, and also some shiny coins or pennies. Now, the reason why these are more shiny as compared to the others is the reaction between a lemon, or in this case, a ripe calamansi, which contains the citric acid. So the tarnished area and the citric acid from the lemon uh, brings out the lustrous or the shiny appearance of the pen. And then for our first theoretical topic, you have the Arrhenius acid-base definition. So I think when you are still in your lower years, you have discussed what are acids and also likewise what are bases. Okay, according to Arrhenius' definition, an acid is a substance that contains hydrogen and dissociates in water to yield hydronium ion. Okay? And then a base is a substance that contains hydroxyl group and dissociate in water to yield hydroxide. So two distinct. The first one is that acid contains hydrogen, the other one contains hydroxyl. And upon dissociation in water, the other one or the acid produces H plus or hydronium ion, whereas for the case of base, the OH negative will be yielded. So then therefore, the reaction of acid and base is called neutralization. So the reaction of H plus ion from the acid and the OH ion from the base forms water to make it neutral. The neutralization is exothermic and releases approximately 56 kilojoule per mole of acid and base. So to be exact, that is actually a release of 55.9 kilojoule. And the meeting of the hydronium and the hydroxyl and the hydronium ions forming water. And then we have also another definition that is by the Bronsted-Lowry acid-base definition. So an acid is a proton donor. I skip the next line. The base is a proton acceptor. So again, the distinction is the acid is a donor or a plus donor or H plus donor, whereas for the case of the base, it is a proton acceptor. It accepts H plus. So it implies that proton is negatively charged, or the base is negatively charged rather. An acid must contain H in its formula, and it is written as a suffix or written before the next substance or the next compound. Whereas for the base, it contains OH, and it is usually written after the, the substance or the compound. That is the Lowry or the Bronsted-Lowry perspective. So acid donate proton, bases accept proton. Acid has H plus in the beginning of the formula. Bases has OH at the end of the formula. So we have here a molecular model showing to you two water molecules. So you have here water, the, the oxygen, the two molecules of hydrogen. This is another group of water. So the theoretical union of the two will yield the H3O, giving an extra H plus, and then you have here the hydroxyl group. From the molecular model that you have seen, this is usually the acid and there is the H plus. And the base is usually in an OH form. So you have here a union of conjugate acid and a conjugate base upon the entry of the mixture of acid or reaction of acid and a base in order to form neutral. Now let us go to the meaning of Ka, or the acid dissociation constant. For the ionization of acid or H+, you have here as the many conclusion. For a weak acid with a relatively high Ka, a 1 molar solution has 10% of Sa molecule dissociated. Now, for a weak acid with moderate Ka, that is already 10 to negative 5. A 1 molar solution with a weak acid has only 3% of the Ha molecule dissociated. For a weak acid with relatively low Ka, take note, the first one is relatively high, and then moderate Ka, and then relatively low Ka. So approximately it has 10 to the 10 value of Ka. Hence, a 1M solution has approximately 0.001% of Ha molecule dissociated. So meaning to say, the lower or the weaker the acid, the lower also is its Ha molecule dissociation. So by formula, you have there as the illustration. So you have heard the Ha of a certain substance added with water. And whatever is this, whether it is a high or moderate or relative, it will depend also on the value of the A. The, the Ka and the Kc depends on the reaction with water. So upon the reaction, water do not already have a certain part of the reaction. So the formula will drop the water and show to you the major characters, the dissociation of acid constant. So the stronger acid has a larger Ka. Now in the electron cloud formula, you can see here the different structure. So you have here the HCl, of course with water. You have here the NH3, and then the dissociation will just simply say to you that it will just simply have one loop uh, reacting with water. Whereas for this case, it has already three loops or is plus. So that is just simply an illustration of how the different molecules could form the dissociation for strong and weak acid, as also illustrated from the following graph. The first one is for the strong acid and the lower one is for the weak acid. So you can see here the strong participation of the formation of acid. Whereas in this case, there is only a few. There are various ways to describe acid strength. One is the Ka value as we are discussing. If the Ka is large, it is a strong acid. If the Ka is small, it is a weak acid. Another is the dissociation equilibrium. If the dissociation equilibrium is far to the right, it is a strong acid. But if the dissociation equilibrium is towards the left, it is a weak acid. So it just follows. The equilibrium concentration of H plus compared with the original concentration of HA. So you have here the illustration. And then also likewise the strength of the base, the conjugate base. A concrete example of the illustration is actually the list here of some acids that we usually use in the laboratory. So these are the six strong acids. You have the halides, and of course you have also the oxo acids. Um, you have here the sulfuric acid or the H2SO4. You have here the nitrogen acid or the nitrous and the nitric acid. And you have also another halide acid here or hydrogen halide, that is the HCl. And this one is the perchloric acid. It has 4 oxygen. The difference of perchloric acid and HCl is that the HCl has no oxygen. It is a hydrogen halide, HCl. Whereas for the case of perchloric acid, it is an oxyacid that contains chlorine or halide, but the amount of oxygen is also greater. Okay, this is just simply an arrangement of the strength of oxygen-containing acids or the oxoacids. So the Cl, if you're going to remember your periodic table, the arrangement with different halogen, FClBri, right? So the Cl is higher or greater in terms of strength. Going down the periodic table is the Br and then the iodine. But comparing between oxo and halogen, the halogens are weaker as compared to the oxo. Okay, we have an example here, the phosphoric acid or the dissociation of phosphoric acid. So phosphoric acid is a weak acid, but please do not play phosphoric acid in the lab. It is still a strong acid and normally loses one proton in a solution, but it has a series of dissociation. So you have here H3PO4 with 3 hydrogen and then with 2 hydrogen and then 1 hydrogen. working with one molecule of water. So all of them has an H plus in the product, but as you can see, you have still the hydrogen ions for H3PO4 and H2PO4. But of course, with the going of hydrogen to water, you have only PO4 in this dissociation. Okay, so where did the other H went? The H3 here fell in love with H2O, making it H3O. So hiwalayan lang ito, no? H2PO4 going to water, you have there the H3PO4. But this one had suffered with the loss of hydrogen. Okay, here are some monoprotic acid. And their concentration, the Ka value, you can see here, it is going upward. The strength or the Ka is, the trend is going upward. So, you have the hydrogen sulfide ion. Usually, these are halogen containing, except for the case of some organic and nitrous. You have also metalloions here, and then phenol, organic. This is organic, no? So these are monoprotic acid. They are acid. They are actually common also in the lab, not only as a monoprotic acid. Okay. Uh, is- Here is also the strength that will show you the acid-base pairs. So this is the of course, as you go up, it is more acidic. As you go down, it is more basic. So the HCl, H2SO4, meaning to say HCl is stronger than H2SO4, and then all will follow. Just as the same with the case of the base. You could no longer question as to their arrangement because these are actually constant. Okay, these are also some illustration of reaction showing to you conjugation of different pairs of elements. So this is actually giving away the hydrogen from hydrochloric acid, so forming the H3O. For this case, it gives off to Cn. For this case, it will become NH3 in order to have the HCO3. So it is just simply releasing the acid hydrogen plus. From H, of course, you know already what will happen. We have discussed this already, no? So and so forth and so on. So this is actually a problem that I will leave to you to, to solve. However, the solution is already there, but please solve it before you go to the solution. And then you have also here some Ka values of monoprotic acid. These are also constants. We have also here polyprotic acid. So yung first slide, the former slide is monoprotic. This one is polyprotic. And then you have here some dissociation constants for polyprotic acid. Commonly used in the lab are your sulfuric acid, oxalic acid, ascorbic acid, or known also as your vitamin C. Phosphoric acid is sometimes used in the laboratory. We do not welcome activity that make use of arsenic acid because it is highly toxic. So this another equation that you should know is the auto-ionization of water. You might have done already some experiments while you were still in high school in the ionization of water. So this is not new to you, but just simply to look into the process or its relationship to ions and the H plus relationship, this could be shown again, especially this equation. No, this is very popular to you. So the Kw for water, the constant for water could be taken from this value. Okay, we have also here some pH scale of common substances. So you have here in the lab the 1M HCl. You can see this at home. Actually, this is yours, stomach acid. So the HCl here is more concentrated as that of the stomach acid, which is also an HCl. And our stomach acid is even more acidic as compared with the vinegar. No? The acid of the stomach is, or the acidity of our stomach is 2, negative 2. And then the vinegar is 3. Now, the milk, which is not actually sour in taste, is near to neutral, but not neutral. And then, of course, the most common example of what is neutral or at the pH 7 is the pure water. Our blood is basic. The ammonia that you use in cleaning is actually basic, very basic. It is 12 NPH, and then the main ingredient for soap, the sodium hydroxide, has a pH of 14 if the molarity is 1. Now at home, you have here some common things that you use at home, and these are their approximate acidity. Beer is an acid, vinegar is an acid, unpolluted rain is not neutral. It has a pH of 5.6. Normal urine has a pH of 4.8, 7.5. The seawater is basic. It could be neutral to basic, but more on chances that seawater that we are collecting in the for lab analysis are basic. Of course, detergent is basic. And of course, milk of magnesia is basic, or else you will not be using the milk of magnesia to treat or in the treatment of hyperacidity. And then the lye. The lye is also used in the kitchen. It is used in many food preparation. And then of course you have the NaOH. Understanding your pH is actually something that is very practical, and it is usually used also for practical purposes. Like for example, you know that your stomach acid is 1.3 and you are suffering from hyperacidity. Then do not drink any more pure lemon juice or any fruit juice with a pH that is related to lemon. Do not eat anymore something that is with vinegar. Do not eat any more paksiw or sinigang. Don't go to the beer house to drink beer or any wine related to beer or alcohol because these are acidic. And then never ever claim that rainwater is neutral. Okay? And if we're going to place them into a mathematical value, this is how they look like. I'm sorry for covering the illustration, but I think you could already imagine that this refers to the acidic, this refers to the basic, and this is for the neutral. And then you have your relationship of Ka and also likewise the pKa. Of course, you know this already, the neutral is 7. So, in terms of pH, ito palagi yung ginagamit natin, no? But for the POH is just a reverse of the pH because what we are talking here is the acidity, what we are talking here is the basicity. So this is just the reverse. Parang you just simply twist that like an electric fan. So here are some acids that you have encountered already that the pKa at normal room temperature supposedly. But here in the Philippines, you have that the ano, 34, especially in Ilocos or 32. So this is for cold countries. So the acid-base character and the pH scale. This is what you are actually learning with your um, going back. The acid-base character and the pH scale. So this shows to you the meaning of the acid in relation to what is being read in the pH meter. And the pH in the pH meter is actually mathematically being presented as the negative log of H3O positive. So if you are asking what is the pH of a solution that is 10 to the 12 m in hydronium ion, it just simply means that that is a solution with a pH of 12. So if you are being asked what is the pH of a solution that is 7.3 to the negative 9 m, then the pH could be translated as 7.3, negative log, 7.3 times 10 to the 9. And that is just simply, since it is negative log, we could refer it as negative 1 also. So negative 1 times log 7.3 plus log 10 to the 9. And then you continue solving for the solution based on your constants and calculators. Now, as a guide, the pH of neutral solution is 7. The pH of acidic solution is below 7, basic above 7. Okay, classifying the relative strength of acid and bases. There are two types of strong acids, the hydroholic acid and the oxo acid. I think we have made mention last time that the hydroholic acid refers to the acid that belongs to the halide. That's why it's called hydroholic. It contains hydrogen and halides. Hydroholic. So the elements in the halides group are the fluorine, chlorine, bromine, iodine. So these are the hydroholic acid. If we say oxoacid, they contain the atom oxygen. And they exceed the number of pores of hydrogen. Like for example, the nitric acid, sulfuric acid, and the perchloric acid. The one that I was telling you last time, that the number of oxygen is higher than the number of hydrogen. Or else, if the hydrogen is higher than the oxygen, this could be classified as a hydroholic acid. But since the number of oxygen is higher than hydrogen, this is still an oxo acid. Okay? There are many more weak acids than strong ones. And this includes the hydroholic acid, hydrofluoric acid, and then you have also the HCN, the hydrogen sulfide, These are strong ones. These are weak ones. And then you have also acids, oxoacid, in which the I have made mention of that already. And then still these are examples of strong acids and weak bases. Strong acids, usually they are found in group A1, metallic, metallic ones, like sodium hydroxide. Sodium hydroxide is one of the most popular bases. Lithium hydroxide. We have also calcium hydroxide. We have also barium hydroxide. These are common uh, things that you will encounter in the lab. And then for weak bases, so these are the strong OH, and then we have also the weak OH. Ammonia is weak. That is usually a common example of weak bases. We usually say ammonia. And of course, some organic bases are also weak bases. And of course, this is an example of a portable pH meter with only one electrode, the pH electrode. There are some pH meter that also have a multi-electrodes. So you could get the pH of two substances at the same time. Or the other one could be temperature, and then the other one is the pH. Okay, there are different methods of measuring aside from the pH meter. You have also the pH paper. Of course, you have also the litmus paper. Okay, these are some things that we usually think of or consider in solving problems that are related to acids and base. Not only acids and base, but other chemical reaction. So think of chemistry if you are thinking about acid and bases, or if you want to identify whether a thing is an acid or a base. Be systematic. You should know the properties of what are acid and what are bases. You should know what are their common reactions or even adverse reactions to yourself. Be flexible. If the experiment calls for an acid but no specific acid was made mention, your vinegar is an acid. No? If it calls for a base, then your soap solution is a base. And you know that. So do not look for expensive ones written in the laboratory manual, but try to be flexible and to be practical, especially if you will be teaching in areas that have limited resources in terms of laboratory facilities. And then be patient. Scientists should always have this, and be confident. Be confident because you always think about the chemistry. And one more thing, understand and think, don't just simply memorize. So these are actually mathematical illustrations on calculating H3O. Don't you worry, you know this already, I will not discuss. So let's go to the different reactions of some elements with acid. You might be doing this in the lab. So you will be comparing the reaction of strong acid with that of a base. So these are the same aluminum zinc metals, but this is a strong acid, and you can see the effervescent that was formed is massive. This is within a weak acid, so you can see just simply a few effervescence released by the zinc method. So you could calculate those things, the strength, by using your ever favorite K. Ka is equal to H times X over Yx. And then in terms of molecular cloud formula, this is hydrofluoric acid. Of course, that is water, no? So this is how you could illustrate in your class that these are the molecules present and they are either acid or base. So if HF is added with water, what is this solution? This is acidic. So you can do some kind of exercises by using some molecular models. Your molecular models do not just be contented with expensive ones. You can have papers or you can have plastic balls or even you can have other indigenous materials that shows of different colors that you could use to show how HCN looks like and H2O and how they react with one another forming a solution. Okay, assignment. You will be doing this. You will also be doing this. Just simply be guided with the role and more concentrated and more dilute in terms of acidity and its reverse basicity. Study the different problems. This is the only way that you could remember your high school pH or pKa or pK uh, expression. It's just like this one. The problem. Hypochlorous acid is a weak acid formed in laundry bleach. So why is it that the laundry bleach could remove some stain? It is because of the hypochlorous acid. But how strong? How could that happen? You can explain it in chemistry by showing this solution. Where have I taken this from the label? No? Or it might be even given in the problem, just like in this case. So these are just simply problems or guides in identifying things related to solving problems on pKa and pK or pH. This is a waste treatment, liquid waste treatment, wherein there are different treatment using acid and bases to make the wastewater safe to be disposed. Okay, all the rest are actually problems. Okay, um, some constants are shown to you from time to time to be guided. How are you in solving the problems? Do you know the effect of metals or salts on pH and acidity? Do you know that sodium or other metals are very strong with bases? Again, these are illustrations. These are still illustrations or mathematical models or their computation. It is just simply it is just simply substituting things within the formula. It's nothing hard. That is just simply algebra. This is another type of pH meter wherein the temperature could be determined, the slope, if you're going to make it in a graphical presentation, could be produced, and of course, you have here the electrode. So from here, you can read from the screen that the pH is 2.93. So if this is aluminum chloride, if the one that is being diagnosed is or the sample is aluminum chloride, the pH of such is 2.93. You will be using or I don't know if you have done already some experiments using the pH meter while you were still in the grade school, but you will do the same using the different electrodes to determine the acidity or basicity. So it is just simply like determining whether an aqueous solution of iron nitride is acidic or neutral. So you could determine it by being indulged with mathematical equation, or you go directly to your pH meter. This is already a review slide. The base donates, the acid accepts. This is on the Lewis acid. This is the magnesium ion as a Lewis acid. So this is the one. And this is within the chlorophyll molecule. The greening of the leaves. Function of this. This is again a review slide showing to you the relationship of different constants. If constant acid is greater than the constant base, of course it is acid. These are also another examples. So you practice your math in order to appreciate the value of the different pH or the pKa or Ka or Kb, but do not usually go to Kw or neutral, or that is for water. So as a summary, you can have this as a guide to determine strong acids and also likewise to know the pH or the dissociation constants.